Good morning and welcome to the midterm webinar for the 80 Challenge. Thanks all of you for joining us this morning or afternoon or evening, depending on where you are in the world. The goal of today's webinar is to show you a little bit in terms of current progress and where we are in the challenge. Oops. And then to give you instructions for final submissions. So what's going to happen in this final month of the challenge. So let's launch right into it. We're going to go through each of the sub-challenges one by one. So we'll start with sub-challenge 1, which is the challenge here was to predict cognitive decline based on genetic data. And so at the time of the midterm or interim leaderboard challenge, which was on the 21st of August, this is what the leaderboard looked like. This actually may look a little different to you than what the leaderboard looked like on the website, and that is because the A team was accidentally submitting more models than their allotted amount. So we have rectified that. We have corrected the leaderboard, removing the extra submissions, and this is the official leaderboard, how it looks with that information removed. And so what you can see is that, in fact, the A team is still doing very well, but that the team ADDT is, in fact, pulled out into the lead with their model. And so congratulations to Team ADDT for how well they're doing on this challenge. But one thing that we have observed is that the clinical model is doing the majority of the work here. So we see that the clinical covariates do a much better job of predicting change in MMSE, representing cognitive decline, than does the genetic model. And as such, and because this challenge is really focused on assessing what the genetic data can tell us, we have decided that it's important that we level the playing field, that everybody has access to the same quality clinical model to build their genetic analyses on top of. And as such, we've asked the A team, who, as you can see, has built a clinical model that beats any of the genetic models that they built, and actually has the best mean rank across the Pearson and the Spearman of any of the clinical models that were submitted by any of the teams. We've asked them to present and provide to all of you their clinical models so that you guys can incorporate that information into your own analyses, and we can really focus on what genetics can do and provide on top of clinical. So I'd actually asked them to present on this webinar to all of you their clinical model and what they've done. And so I'm going to just turn it right over to them. Let me pull up their slides. Oops. Yes, here we go. And I'm going to unmute them, so each of you is on mute. And I'm also going to ask all of the rest of you, if you have any questions, please write them into the question box in the webinar. If you have questions for us or you have questions for the A team or any of the other presenters, that's the best way to get them answered. Okay, so now I am unmuting the A team, and my understanding is that Chester is the one who will be presenting. Hello? I've unmuted Qian Yu. Are you
I'm
there?
here. I'm
Hello.
hearing you. Hi.
Are you presenting, or are you in the room with
Chester?
Chester?
I believe he is in, but I cannot tell why he didn't answer.
I see. So he's not here yet, right? Okay. Well, we could come back to you, I guess. Would you be comfortable?
Yeah, I will check with him right away, and maybe we will be ready. Otherwise, I can make the presentation.
Okay. Well, perhaps while we're waiting, Ben, you could give us some reflections and show your slides. How's that?
That sounds good. Thanks, Laura. I just have a couple slides that I wanted to show, and mainly having to do with the one of the challenges in terms of identifying additional signal in the ADNI and ROS-map data sets in terms of predicting delta MMSC. So in Alzheimer's genetics in general, it is pretty well known that aside from the ApoE locus, the predictive power of any genetic marker is not particularly high. And so if you go, actually, could you go to the next slide? So this is a Manhattan plot of the sort of just pairwise the p-values from pairwise correlations between every single marker in the, I guess actually it's not every single, it's like 6 million markers across the whole genome, and Alzheimer's disease case status. And while the p-values may look impressive in terms of their association with, so just to explain to everyone, to be very clear what this plot is representing, every single dot represents the p-value from a test of association between a marker at a given location on chromosome 1 through 22 and ADK status. And the more significant the p-value, the stronger the evidence that there is a significant association. This plot was generated using data from over 74,000 individuals. And even with 74,000 individuals, you end up only cumulatively explaining around 8% of the variation in Alzheimer's disease. So, and 6% of that is explained by the ApoE locus. So we're really only talking all these other loci, of which there are about 18 or so, only explain about 2% more of the variation in Alzheimer's disease above and beyond than the ApoE locus. So what we're looking at with the ADNI and ROS-map data is a much smaller sample size. So it's going to be very difficult to have enough statistical power to identify loci de novo within these data set that are predictive of phenotypes relevant to Alzheimer's disease, such as change in MMSC. So one strategy that it's on the tips and tricks page on the challenge webpage that I've mentioned before, or that I've discussed this sort of idea on that page, is that instead of trying to learn models where you do feature selection based on, you either do feature selection or you just learn a model with all the data at hand, you actually do some sort of informed feature selection or choice of a prior, as it were. And one, obvious example is to use the data here presented in terms of the IGAP SNPs. So one suggestion that's been made, and we've actually observed in the dry runs, is that 3 of these SNPs associated with these genes that are shown on this plot add about 1% in the terms of the correlations between the clinical versus clinical plus genetic models. So we do think that there is some genetic signal, though that genetic signal may be highly located in these regions that are more likely to be relevant to the disease based on these other data. So one thing I would suggest going forward after everyone gets the clinical model from the A team is to think about how to do this feature selection in a way that is relevant to the problem at hand, and specifically using these sort of high quality data sets like the IGAP. Actually, could you go back to the previous slide? And to come up with better feature sets. And so there are many ways of doing this, and I don't want to tell you the best ways because we don't know the best ways. But one thing to think about is other diseases that are comorbid with Alzheimer's disease. So, for example, metabolic syndrome, hypertension, insulin resistance. These things are known to be comorbid with Alzheimer's disease, and they have their own genetic associations in terms of what's been identified previously by these GWAS type data sets. Another possibility is to focus in on the pathways that have been identified in the IGAP paper and try to build on that. And I mean, these are just some very general suggestions, and we don't know how they will do. But it seems that instead of trying to do a very high level, use all the data at hand approach and try to just de novo learn a predictive model, incorporating good genetic prior information, I think, is going to be absolutely key in terms of improving over these baseline clinical models. So those are just some thoughts that I wanted to share with the challenge participants. I would greatly appreciate if you have any feedback or thoughts on this, and if you want to share your strategies for producing these sorts of feature selection procedures that are informed by the actual biology of the problem, that would be greatly appreciated, I think. And I guess with that, I will turn it back over to Laura to continue the discussion.
Yeah, so if we can all start with the best performing clinical model and then start thinking about how to appropriately feature select on the genetics, as shown here, we're really interested in what that can add to the model. So if you're interested in talking with each other about feature selection, you can use the forum. Also, if you're interested in talking to us about feature selection, the forum is a good place. You can also walk down the hall at your university and look for somebody who knows something about AD biology or ApoE, lipoproteins, who may be able to help inform your analyses as well. So in our experience, we don't find that biologists can solve this problem or that informaticians can solve this problem alone, but it takes the combination of the two to get a really sound feature set that can then be used with the best possible machine learning approaches. So we encourage you to incorporate both of those modalities into your teams as you try to solve this problem. And as Ben said, we do think there is genetic signal here. We did do our own analyses that suggest that although small, there is some genetic signal here, and we're really interested in your creativity and efforts to identify the most possible genetic signal. So let's see. Chinyu, have you found Chester?
Yeah, I believe Chester is in. Could you unmute him?
I don't see his name. Would it be something other?
Yuchen Zhang.
Yeah. Okay. Let's go back to your slides here. Okay. Okay. So now I am unmuting. Chester, are you there?
Hello.
Hello.
Hello, I'm Chester.
Welcome. Thank you for taking the time to present your approach with us. I can move your slides forward if you would like to take us through them.
Okay, thank you. Should I start?
Yes, please.
Okay. We are a team, and we all come from the National Taiwan University, and I'm Yuchen Zhang, and you can call me Chester. Okay.
Okay.
Okay. We build a base clinical model in Leaderboard, so many people is curious about how to build it. So today I will introduce the pipeline of the base clinical model. A according to this introduction, you will get some idea about how to design of the feature set and how to do feature selection and the way to ensemble the different models. Okay. Okay. So first we do the design of the feature set, and we can find there are several useless features. So we delete them first, and then we link the baseline data with the 24 months follow-up by patient ID. So next. Yes, this means deletion. Okay, so we combine the MMSE 24 with the baseline data. Okay. Second, as the previous study, if we transform categorical variable into binary feature, then we can get better performance. So we transfer categorical variable into binary feature. For example, we transform diagnosis baseline to CN, LMCI, and AD. Click. Yes, we separate them to like this. And the gender will transform to numerical, 1 and 0. Okay. Okay. Next. Thanks. Third, we separate APOE genotype in 3 different features. I think this is most important idea for the best clinical models. Before we separate APOE genotype, we can get only 0.16 in Pearson correlation for previous model. But after we separate APOE genotype, we can get 0.14 Pearson correlation. So I think this is the most important ideas for this model. And so APOE genotype has 3 different kinds of alleles: APOE2, APOE3, and APOE4. So we separate APOE genotype to 3 features. And the value of these features is set to integer 0 to 2, standard for the allele numbers in subjects. So next. So after transform, you can find this is our feature set. So finally, we produce 10 feature set. Okay. Okay. Then next, we do feature selection. We conduct univariate analysis and linear regression to select features. Univariate feature selection works by ranking the feature based on the F-test. After univariate feature selection, we can get F-score. And the F-score can be regarded as the weight of the features. As same as univariate feature selection, the linear regression estimate coefficient of linear combination can be also regarded as the weight of the feature, as shown in this table. Since during competition, the feature value corresponding to APOE2 and APOE3 were not initially released, and according to our corresponding validation results, reveal that these 2 features really contain valuable information. So the baseline feature set for building our prediction model include all the 6 features that will rank before APOE2 and APOE3. But we then add the age into the baseline feature set because it is well known that AD is an age-dependent disease. So we add the age to with the previous features. So the last three features, we think these three features is not important. But in the real situation, we don't know which feature we must remove. So finally, we combine the previous features and the combinations of these three features to build the selected feature set. Okay, next. So as you know, there will be 8 different kinds of feature set. It's the combination of the LMCI and the education and the gender. So all of the selected feature set will train with Epsilon SVR with RBF kernel, and we perform a five-fold cross validation and grid search the parameter for each of the models. Okay. Okay. So finally, at the final stage, this title must be the way to select model for ensemble. Sorry. So the main idea we use is baking meta estimator. The driving principle is to build several estimators independently and the average meta prediction. The combination usually get better because its variance is reduced. So we have 2 ways to selecting model for ensemble. The first is just randomly select and average. The second is you can use the cross validation of the training data set as a guideline. For example, you can use R-square, mean square, or Pearson correlation, and to lead you to select the model for ensemble. Okay. So finally, you can get a final model to prediction a result. This result is our base model in the leaderboard. Okay, thank you.
So thank you very much for presenting that and providing that information to the rest of the excuse me, challenge participants. A written description of this will be available on the website, so all of you can consider these ideas in integrating them into your own approaches moving forward. And so we are very curious to see whether this improves the models across the board, both the presentation of this clinical information, this clinical approach, and some of Ben's suggestions regarding the use of genetics. Okay. Okay, so that's question 1. Just to reiterate, we're really interested in benchmarking progress, particularly for this sub-challenge. We want not just to see who can build the best model, but really to assess the degree by which the genetic features are meaningfully contributing to your predictions. And so we want everybody to try to start analysis with the best possible clinical model and build on top of that with genetic features. And as such, we are going to require that in order to win, a model needs to beat 2 benchmarks in a statistically meaningful manner. One is the best clinical model as provided by the A-team. And the second is a very simple genetic model that we will be providing, which builds on top of that clinical model by including just a couple of the genotypes in the IGAP SNPs. And really, this is a very simple genetic model. It was built in one afternoon by a set of undergraduates in Utah. And so I trust that every single one of you will be able to beat that. But we want to put a little benchmark out there. And so there you go. Okay, so moving on to sub-challenge 2. Here's the leaderboard for sub-challenge 2. You can see that Team ICM CUDA Dreamers are leading this leaderboard. Unfortunately, they were not able to make it today. They had a conflict. Also, they're in, in Poland, but they they did send a couple of slides describing their approach and including their contact information. So if you have any questions about their approach or suggestions for them, or you think what they're doing is interesting and you might want to collaborate with them, here is a way to get a hold of them. So this team, as I said, comes out of the University of Warsaw in Poland, and it is led by Witold Rudnicki. And so here is the approach that they took. So there's a couple of steps for feature selection on the genotypes based on quality, correlations with other features, etc. And then so that looks like the main finesse in their model is the way in which they're feature selecting. And then they're using random forests to look at modeling. And so the main issues they've run into are listed here. As many of us have found, there are a lot of features and many of them are not necessarily relevant. Some are relevant only in the context of some of the samples and not others. Overfitting, of course, is always an issue. And the balanced accuracy measurement is indeed dependent on the unknown class balance. So if you're interested in learning more about this approach, please contact this team directly through this email. All of these slides will be made available on the website afterwards, as will a recording of this webinar, so you can come back to look at these in the future as well, if you're interested in contacting them at that time. Okay, so with that, let's move on to question 3. So I have Arno Klein here, and he will be taking us through this. What I'm showing you here is the leaderboard for question 3. You can see in this case, we have both the best model, which is by the Guan Lab, as well as a benchmark that we built ourselves, which is below that. And you can see that several of you are actually beating that benchmark. So congratulations to all of you. I'll turn it over to Arno at this point.
Yeah, hi everybody. So it was fun getting involved in this, and my colleague Elias will be speaking in just a moment. He went ahead to try and set a benchmark, and in doing so, he threw out all the covariates, the genetic information, demographics, clinical, everything, except for the imaging features, because what distinguishes this sub-challenge is the use of the ADNI and indeed the AdNeuromed leaderboard data. So he set the benchmark, and I believe that after he got back from lunchtime, somebody beat the benchmark, so that's good. I'm assuming, I hope, that people are availing themselves of the other data that accompany the imaging data. But first I'm going to have Elias speak briefly about the predictive models that he put together for the benchmark, just to give you a sense of where things should go from there.
Okay. Yeah. For the benchmark, I did something very simple. So it's actually an ensemble model. It's a stacked regression of Ridge regression, lasso, and elastic map predictors. So I fit Ridge regression, elastic map, and lasso, and I just got a stacked version of using Braman's approach for stacked regression. And instead of actually using the non-negative least squares approach for the non-negative weights, I actually use simply Ridge regression again. So yeah, that's the baseline model, and as Arno said, it only uses the image data, no covariates whatsoever.
Yeah, and I would love to hear in detail what all the labs, all the teams are doing to tackle this problem. But we only have time for the Guan Lab at University of Michigan to present a few slides. And I would hope that they would, in their description, give us an account of how this current work on Gaussian process regression models differs from the accomplishments in previous challenges. And so we'll follow up those slides with a few questions. And of course, if anybody listening has further questions, we welcome those.
And you can write your questions in the little question box. So, okay, I'm going to unmute Wanfeng Guan. Will you be doing the presentation today?
Yeah.
Hello, welcome.
Hi, thanks, Laura. So I'm going to present our strategy for the AD challenge. Next slide. Just a very short introduction of my lab. The research in my lab focuses on functional genomic data integration, including protein function prediction, biological networks, and multiple levels of data integration. For details of our research, please visit our website. Next slide. We deeply believe that innovative solutions are most likely to arise in a competitive environment such as DREAM, and that is why we participated in these community-based benchmark studies. For DREAM, so far we have participated in the 2013 Network Inference Challenge and the 2014 Drug Responder Challenge, and so far we have done pretty well in those challenges. Through those challenges, the most gain for us is that we have accumulated a suite of algorithms that we know should perform reasonably well. Next slide. In this AD challenge, our team consists of 2 people, my student Fan Zhu and myself. Next slide. The method we used in all 3 sub-challenges is called Gaussian process regression, GPR, which is a classical interpolation regression method. In one sentence, we try to find out the similar patients among all other patients, and only use these patients to predict the outcome of unseen test patient. Next slide. GPR is an excellent model in population genetic studies. We developed it in the context in the recent DREAM rheumatoid arthritis challenge. In this table, Team MI used Gamma, which is perhaps one of the most influential software in population genetics today. Gamma was originally published as a method paper in PLOS Genetics, and then again as application in Nature Method and Nature Genetics. Twice. As expected, it performs exceptionally well in the RNA challenge, but this GPR model was able to beat Gamma in both sub-challenges. Additionally, Gamma's training time is 4 to 5 hours on the RNA challenge dataset, around 1,000 training points and 600 testing points. GPR's prediction time is 1 minute for 600 patients, or less than 0.1 second per patient, making it an exceptional candidate to be used in real-time clinical settings. Of course, as just has been discussed by Lara and the A team, in all these models, genetics is not contributing much on top of clinical models. I think it is not that genetics are already completely reflected by clinical information. Instead, a fundamental method is still needed to select relevant SNPs for genetic studies, which I think is likely to arise in this competition environment, even probably is not going to be by my team. Next slide. So there are several reasons that I think GPR is an excellent model in this situation. First, it finds the similar people instead of establishing a model over all people. This makes sense because it is possible that the data from European people may look totally different from Asian, and women may totally look different from men. Then a traditional regression method would lose its power under those circumstances. But it's highly unlikely that one cannot find someone that is similar to you in the training population. Secondly, it is a local regression instead of a global regression. Based on my observation, human-created artificial data, such as microarray RNA-seq, tends to follow linear relationships. If they are not linear, people tend to make them look like linear. However, biological data created by nature tends to follow either logistic relationships or form clusters. GPR in this case is an excellent model to deal with clusters. For example, in linear regression, neural network or SVM, all of them actually use the same stochastic gradient descent to solve the target function. So to me, they are essentially the same algorithm that was developed by Isaac Newton 300 years ago. Only the very peripheral part of it is changed. So cluster examples will contribute more than scattered examples in those regression models, in SGD, in models that will be solved by SGD. So GPR was invented by Danny Craig in his 1950 master's thesis. So GPR is also called kriging in memory of this great scientist who passed away last year. By a local regression, GPR can successfully downweight the clustered data points, which I think it will surely occur in human population. So thirdly, because it is a local regression, differences between study cohorts will naturally be taken care of. This effect probably won't be seen in this AD challenge, since the testing cohort is pretty homogeneous population. But it was clearly seen in the previous RN challenge. And I would say it will no doubt to be seen in a practical clinical setting. Next slide. So the potential of this GPR is huge. We have used it in the RE challenge on genetic and clinical data, and here on the image data. I think it has huge potential to scale up to millions of people because of its k-nearest neighbor properties inherited in this model. So the fastest k-nearest neighbor algorithm, K-graph, currently held here as a private business Arbor algorithms, it can achieve a searching speed of less than 0.5 seconds for 1,000 individuals. Combined with K-graph, the GPR model we developed can be deployed with millions of individuals in a single click on the fly. So I think this speed is needed when making instant predictions in clinical settings. But it will be very difficult to be achieved by any alternative method. So that's my presentation. Thank you.
Thank you very much. If you could address a few questions that we have off the bat. One is this is clearly comes in the heels of the RA challenge. Could you please give us some sense of how your approach differs from your prior application of GPR to the RA challenge or the breast cancer challenge, and what data you made use of? Did you make use of the genetic data or other covariates?
Oh yeah, of course. So essentially, it has no difference from the RNA challenge that we developed. So the only difference is we put no genetics. We put clinical and image data together and just concatenate them together into our model. So as for last year's breast cancer, that is totally a different model. So that is essentially a linear regression model with some denoising properties.
Oh, thank you. That preceded my coming to SAGE. And how did you choose the covariance function for your Gaussian process?
So that is through cross-validation. So clinical. So yeah, that is. Let me ask my student what is the covariance function here. So he's typing to me. So.
Oh, great.
You know, we can just we can unmute him. Why don't we do that?
Oh, okay.
Lufana, I'm unmuting you as well, so you can answer directly. Hello.
Oh, he said he doesn't have a mic.
Oh, okay.
That won't help then.
No.
Okay, he's going to type me the percentage of contribution of each variable, and I will tell you about that.
Okay, thank you.
So for the RA challenge, as I remember, it's 40% for the clinical, and the rest is the genetics. And for this one.
And you reach that percentage through the cross-validation?
Yeah, it's just through cross-validation. Oh, and cross-validation on the validation on the leaderboard.
I see. And did you
What was which covariance function did you use, and which parameters does it involve?
He said he's checking, so
Okay.
Okay. In the meantime, you said you concatenated the clinical covariates with the image features. Did you
oh, okay, I got it. So 20% for APOE, volume is 50% for education. So just one comment from this model. I don't think education really contribute that much. We probably should turn this variable down a little bit.
Yeah, actually, that's since you raised that point, you might remember from earlier discussion on a webinar that the training and the leaderboard test sets are different, the ADNI and the AdNeuromed data. And two of the ways in which they are distinctly different is the educational level and also the age distribution. So the fact that you're not able to do prediction well with the using education level is probably not surprising.
Yeah, I think we should turn this. Yeah, I'm telling him we should turn this down a little bit. So I think there was one problem that we encountered during the prediction.
Please.
So I think in one of the I cannot remember which task is that, but in one of the tasks, the training age is the starting age and the testing age is the death age.
Oh, I thought we fixed that.
That's sub challenge 2. Okay.
I thought we fixed that, but we'll.
Isn't that a little bit weird?
Yes.
What?
So I do recall that there was this issue that the ages were recorded at different times in the different studies, but I did think we had corrected that. I'll look into that.
Oh, really? Okay. So one thing we tried was to since there was a difference between the diagnosed age and the death age, so we tried to regress it with the life expectancy provided by the Social Security. But actually, that dropped the performance. So that part we really don't understand because it's not something that we expected.
Sure. Well, thank you for raising that. As Lara said, we'll look into that, make sure we rectify that.
If possible.
If
thank you.
And I was wondering, since each of these challenges usually has an interesting balance when you invite a community of eclectic experts in different domains, you never know how much of a given domain will contribute to the best solution. In looking at these data, given that it's wildly different in terms of its domain than in the previous challenges you've contributed to, did you bring to bear any side information about Alzheimer's or about the brain? For example, when you looked at the image feature data, did you select any given features or weight them differently, or was it done agnostically?
Right now, they are just weighed similarly, but I think that's a great idea to weigh them differently. By cross-validation, so my student said. Yeah, I think we just determined by cross-validation.
Sure. Okay. Well. Oh, another question from Elias.
Yeah, another question. So for the first piece of the challenge, the classification, did you use Gaussian process classification?
Yeah, that's what we used. So you mean for the first challenge?
No, for the first for the classification question of the diagnosis.
Oh, sorry. So there's.
For the second one. That's the second challenge.
No. Sorry. In the sub challenge 3, there are two measures that you came up with: MMSE and diagnosis or classification. So Elias.
Oh yeah. I remember that we discussed that before. So I think the evaluation is only on correlation. So right now, when we assign something to, it's just a linear cutoff. But we did not tune that parameter since it's not used in evaluation. The binary cutoff, yeah. That one was not tuned at all.
Okay, well, thank you very much. I appreciate your going over the slides, and I'd like to also say to everyone else who's on the call, we're sorry that we don't have time to go through each, but there will be opportunities later, and I wish you all the best in continuing to jockey for first place.
Yes, thank you. Thank you to all of the teams for your efforts in the challenge, and for those of you who presented today, thank you for taking the time to do so and for being willing to share your ideas before the challenge is actually over. You know, we are trying to create a community here, and that is a great first step towards that. If anybody else on the call wants to be put in contact with any of the teams that you heard from today, please just drop us a line, and we'll make sure to make those introductions, or of course you can always use the forum. So in the last couple of minutes, we will just go through some instructions for file submissions, and again, if you have any questions, please write them and we'll get to them. Okay, so we are in the final stages of this competition, this challenge. Final submissions will be due October 3rd at midnight Pacific time. The test data is going to be released just under 2 weeks before that, so on September 19th. Each team will get 2 submissions per sub-challenge. We know that there's been a couple of various bumps along the way in this challenge, and so we are open to the idea of extending these deadlines if you all as participants think that this would be useful to you. So if that is true, please let us know in the forum, and we will assess how many of the teams would like an extension, if any, and we'll consider it. Okay, so what does final submission look like? Of course, you need to submit a prediction file, and we will be providing templates on the website. You need to provide a written description of your methodology, and this can be done in your Synapse project in the wiki. You need to provide your code. One of the major tenets of the DREAM challenges is that we're trying to provide reproducible transparent research. So it's important that we have not just a written description of what you've done, but actually the code. So anybody who wants to adopt your ideas or think through your concepts can go back and look at exactly what you've done. And the final thing we're requesting are files that can be used for a supervised ensemble analysis of all of the results that come in. So one thing that's come out of previous DREAM challenges is this idea that an ensemble of predictions does a better job usually than any individual prediction. And we have just used some simple unsupervised approaches to do ensemble analysis previously. And in collaboration with Gaurav Pende, who's at Mount Sinai, we've been considering some supervised approaches. And so in order to do that, we need a couple of extra files from you. One is leave one out cross-validation predictions on the training set itself, as well as predictions for the leaderboard using the exact approach that you end up using for your final prediction for the test set. All of the details of exactly what we need are explained on the website. We're building out that web page, that wiki page right now. So by the end of the week, it will have templates for all of these files. There is already a template for how you can put your written methodology in. Of course, your code, you can just use whatever sorts of files you already have. And then the final thing I'd like to say is once this challenge closes, we will spend a couple of weeks looking through and analyzing all of your submissions and identifying who is winning each of these challenges, not just by who has the best score, but looking to see whether it is actually statistically better than any of the others, trying trying to get an assessment for how you're doing as a group and how the winning team might be doing relative to the others. The next stage after that, of course, is to turn all of this into a written document, a manuscript that can be submitted to Nature Neuroscience. And in the previous challenges, we've done that ourselves with just the winning team participating in the writing. In this case, we'd like to open that up to all of you. So there will be what we're loosely calling a community phase, which probably won't involve additional analyses, but will involve discussions about the results of this challenge and maybe some post hoc analysis on the predictions that were made during this phase of the challenge. And so there'll be some more details coming in the future, but the idea is that we can all work together, not just on the building of models, but also on the assessing and interpretation of the results that all of you produced. And that will include ensemble analyses. So I know many of you are interested in ensemble approaches. We are creating these ensemble these files that can be used for supervised ensemble analyses. Of course, you are welcome to try your hand at this as well as, we will be doing so, but we would welcome your contributions to that as well. So more information about all of that is coming. That will be the next phase of the challenge after October 3rd. So let's see. Well, let's just end. There's a couple of questions. So let me go through these. Let's see. Can you share the slides? Yes, absolutely. We will do so through the webinar as well as the recording. Do you have information on ethnicity? I believe if we had information on ethnicity, we would have released it. So I think that we do not, but I will check into that and we will let you know on the forum. If this webinar is recorded, will it be available to view later? Yes, we will put a link to it on the forum and on the webpage in the news section. So that's it for questions. Arno, do you have any last words?
No, thank you very much. And also be prepared. More people are getting invited to this challenge.
Yeah, absolutely. Good luck in the last month of the challenge. We're excited to watch your progress through the leaderboards. Thank you.